Hello, statistics students. In this lesson, we're going to take something that we learned in the last chapter, a binomial distribution, which is discrete, and something we're learning this chapter, which is a normal distribution, and we're going to combine them together. We're going to learn how to use a normal curve to approximate a binomial. So first thing we should probably do is review the two important components here. We're going to review the central limit theorem and binomial probability. So the central limit theorem says, given any population with a mean and standard dev, mean of mu, standard dev of sigma, whatever those are, if n is big enough, then the sampling distribution will be approximately normal with a mean of mu and a standard dev of sigma over root n. Now there are a number of distributions we can look at. Here's a uniform distribution for rolling a die. Each of these numbers has a 1/6 chance of occurring. Here's the uniform continuous distribution. Every number between 0 and 1 has the same inclusive, has the same chance of being selected. Here's an exponential distribution, and here's a normal distribution. Today we're going to focus on normal and how it can apply to the binomial. So you might recall the 4 components of a binomial experiment. There must be a fixed number of independent trials. There can only be 2 outcomes. One we'll call success and one we'll call failure. And the probability of success has to be the same for each of these independent trials. And then we'll let X be our random variable that represents the number of successes we're going to get. Again, an example of this might be flipping a coin 10 times and wanting to know the probability of getting exactly 7 heads. Well, we have a fixed number of trials, 10. They're independent, assuming because getting a head on this time shouldn't affect whether you get heads the next time. There are 2 outcomes, heads and tails. And the probability of success, probability of getting heads, is the same each flip, 1/2. Another example of a binomial experiment is rolling a die. If we roll a die 3 times and we want to get a 4, let's see that it meets the requirements of a binomial. There are a fixed number of independent trials. There are 3, and each die roll is independent. There are 2 outcomes, success and failure. Well, there's 4 and not 4. And the probability of success is the same for each trial. Probability of getting a 4 each time we roll is 1 out of 6. So we can let X represent the number of successes, and we want to know the probability that X equals 0, 1, 2, or 3. So the formula for binomial probability is n choose k times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So if we have no successes, 1 success, 2 successes, and 3. And it makes sense that our curve would look like this, or our distribution would look like this, because the average value, the average number of 4s that we're going to get in 3 rolls is 1/2. I mean, think of it. It would take 6 rolls on average to get 1 4. So if we only do 3 rolls, we're going to get, on average, a 1/2 of 4. So you roll 3 times, count how many 4s. Roll 3 times, count how many 4s, et cetera, et cetera. Keep doing that. On average, you're going to get a 1/2 of 4. So 1/2, that's the tallest bar, because 1/2 is in here between 0 and 1. How could we use a spreadsheet to confirm these 4 probabilities? I have an extra credit problem coming up eventually, but essentially you could simulate rolling a die 3 times, count those up and graph it. And you should get a graph similar to what we did there using the rand between function on your spreadsheet. So in general, though, a binomial distribution is going to look like this. If you have n trials, you can have 0 successes up to n successes, and it's going to come up to a peak and then trail off. The way I've drawn this one, the probability of success appears to be less than 1/2, because you can see here's the peak, and this trail goes off longer over here than over here. If probability of success is exactly 1/2, then the curve will be symmetrical. It'll peak right in the center. If probability of success is greater than 1/2, then this peak will slide over here and it will trail off to the left. If you need more review, please consult your notes from the previous chapter or watch the earlier video on the binomial distribution. So let's start working an example here, or we'll do a example. So we're going to randomly draw numbers out of a hat, and those numbers go from 1 to 10 inclusive. We're going to say success is a 7. We're going to draw 5 times with replacement. Remember that when you do it with replacement, that's going to give independence. What's the probability that we're going to draw exactly 2 7s out of 5? Well, there's 5 choose 2, probability of success raised to the number of successes. If we're doing it 5 times, there's our number. If that's the number of successes, that's the number of failures, that's the probability of failure. Turns out there's a 7.3% chance that if we have numbers from 1 to 10 and success is a 7, if we draw 5 times, we're going to get 2 successes. There's our probability. So remember these numbers. We're going to draw 5 times, and we want 2 successes. Let's multiply everything by 100. So now we're going to draw 500 times, and I want to know the probability of getting exactly 2 successes. I'm sorry, 200 successes. Do you think the probability is going to be the same? Turns out no, because if you look at the distribution, if we're drawing, how many did we do? We drew 5 times. That means there's going to be 6 rectangles, 0 successes, 1, 2, 3, 4, or 5. How tall was that 2 rectangle? Was 7.3%. Well, if you do 500 times, now you're going to have 501 rectangles, 0 successes up to 500. Now, if we wanted exactly 200, can you see that that 200 rectangle is obviously going to be a lot smaller than 7.3%, because you have to spread that 100% over a lot more rectangles now. But we could figure out the probability. And here's where the problem is. What to do? Sad face. Why is that a problem? Why is that a sad face? Well, I'll take out my handy dandy calculator. Zoom in so you can watch what happens here. What is it doing? Huh. Wow, doesn't seem to be doing anything. What's going on? Well, it turns out 500 choose 200 is bigger than 10 to the 100th power, so it overflows the calculator. Number's too big to handle. So sad face? No, don't be sad. We're going to use the normal approximation to the binomial. All of that was just the prelude to today's lesson. And yes, prelude is the correct pronunciation, not prelude. So the normal approximation, Well, here are some issues. The normal curve is continuous and the binomial is discrete. Yeah, but if you go back to that last example, if you have 501 rectangles, that's a lot of rectangles. We can kind of pretend that that's continuous at some point. And the normal curve is symmetrical, but the binomial distribution is not symmetrical unless p is 1/2. So how can we use the normal distribution to approximate a binomial? Well, here's how we're going to do it. First thing we have to ask ourselves is the situation binomial? If it isn't, if it doesn't meet those 4 requirements, then we clearly cannot use the normal approximation to the binomial. If it is, are the expected number of successes, n times p, and the expected number of failures, nq, or written as n times 1 minus p, greater than or equal to 10? In our current textbook, it says greater than or equal to 5. Not too many textbooks say that. 10 is the better number. So please go to page 275 and 278 if you're using our current elementary statistics picturing the world book, and make those changes. If these 2 conditions are yes, then you can use the binomial approximation. And we'll say that that binomial distribution, even though it's skewed, the part where the bump is close enough to normal that we can approximate it. And that normal approximation, so approximately normal, will have a mean of n times p, and n times p is the, you might remember that as mu, the average number of successes of a binomial. So it'll have a mean of n times p and a standard dev of square root of npq. Now you can go back in that same book, check chapter 4, page 209, to review a little bit about that, but not necessary unless you want to just get that for your own knowledge. So now we have a normal curve. We know its mean and its standard dev. We can start calculating probabilities. Now, why would we want to use the normal curve? Well, 2 conditions, 1 or 2 situations. There are way too many calculations of the binomial probability, or that binomial coefficient n choose k is so big that we get an overflow error on the calculator. So let's take a look at an example where there are way too many calculations. We already saw what happens if it's n choose k is too big, we get an overflow error. So now let's see what happens, why we might want to use a normal approximation. Let's roll a die 600 times. What's the probability of getting more than 125 ones? Well, if you graph your distribution from your binomial probability, you're going to have 601 rectangles in your distribution. From k equals, your number of successes is 0 out of 600 times, you get no ones, all the way up to 600 ones. So what's the probability of getting more than 125? Well, you'd have to do probability of 126, plus the probability of 127, plus the probability of 128, et cetera, et cetera, et cetera, all the way up to 600. Or we can cut that down a little bit using a complement. You can say it's 1 minus the probability of getting up to 125, but you still have to do 0 successes, 1 success, 2 successes, all the way up to 125. Calculate those probabilities, add them up, subtract from 1. That's a lot of calculations, even for somebody like me who loves this stuff. So way too many calculations, sad face. Also, n choose k, man, that's going to be rough. So can we use the normal approximation? Is NP greater than 10? Well, n is 600. The probability of success, if we're rolling a die and we're looking at ones, the probability of success is 1/6. The average number of successes would be 100. That's bigger than 10, greater than or equal to 10. And the average number of failures is 500. which is greater than or equal to 10. So we can use the binomial approximation. And remember, our normal curve will be, our distribution will be approximately normal with a mean of NP, that's our at mean, and our standard dev of square root of NPQ. So this is the number of success, I'm sorry, number of trials, probability of success, probability of failure, multiply them all together and take the square root. So I've kind of drawn an example of that rolling a die 600 times and trying to find the probability of getting a 1. There's very small chance of getting 0 successes out of 600. It's going to peak here at 100 because n times p, 600 times 1/6 is 100, and then it's going to trail off to 600. Well, you can see there's so many of these close to 0 out here and here that where this curve is, even though it's not symmetrical, it's close enough for an approximation. Because just that rule of thumb, NP and NQ are greater than or equal to 10. So if I wanted the probability that X is greater than 125, then I have to say that that's equal to the probability that X is greater than or equal to 126. Now we have the fun part. We have what's called the continuity correction. We have to make this continuity correction because we're taking a discrete distribution with these rectangles, and we're approximating it with the smooth, continuous normal curve. So if I wanted the probability that X is greater than or equal to 126, you see how this rectangle right here, I'd only be getting half of that rectangle if I did X equals 126. So I'm going to zoom in on the 125 here. If I want X is greater than or equal to 126, the way I've got the rectangle centered on 126, you see if I did my normal curve, I'd only be getting part of this rectangle. I need to account for the other part of the rectangle. So the continuity correction, I have to go halfway between these numbers, right here to this line. And that's going to be continuous curve. I'm going to say 125.5. And you say, well, you've added in this little extra area under the curve. Yeah, but you see, I got this little piece here that cuts off. That kind of sort of evens out. And again, it's going to be pretty close for approximation. So we have a z-score, x minus mu over sigma. My x is going to be that continuity correction number. My mu is 100. And here's my sigma is the square root of NPQ. 600 trials, probability of success, probability of failure. So I have a standard dev of 2.79. So the probability that I get more than 125 ones out of 600 is equal to, now this is the discrete one with just the rectangles. When I do it with the normal curve approximation with continuity correction, now I'm doing X is greater than 125.5. So here's my problem stated in terms of X. Well, actually I did X both ways, discrete and continuous. Restated it in terms of Z. Didn't draw my picture, I should do that now. So here's X, I'm sorry, this is 100. And on 125.5, what was our, 500 divided by 6, take the square root. All right, well, I know it's going to be 2.79 standard devs. So it's going to be way out here is 125.5. And I want this area to the right. So the probability that Z is greater than that is 0.0026 or 26 hundredths of 1%. Remember, anything that has less than a 5% chance of happening, we say is unusual. So we would say that this is unusual or unlikely to happen by chance. If you got more than 125 ones out of 600 rolls, either you just got a very fluky sample, and there's a very small chance that that happens. More likely, your die is not a fair die. Right here are two example problems. We'll go over those in class, assuming that we are using the same book when you watch this video. So that is our first part of binomial distribution. The next question is, which way do we move the continuity correction and why? So let's say that I had a distribution that looked like this and the numbers are going down, down, down. What I want the probability that X is greater than 110. Discrete, so I want this rectangle plus this rectangle plus this one all the way out, whatever n is. Well, also discrete, greater than 110 is 111, 112, 113. So that's X is greater than or equal to 111. Now that 111, if I go here to 111, you see I'm only getting half the rectangle. In order to get the other half, I have to scooch it to the left to get 110.5. Here's mu, here's sigma. So my z-score for the probability that X is greater than 110 on that discrete case, using my normal approximation, X minus mu over sigma. Now let's say, we've moved it to the left. Now let's say I want to know the probability of getting exactly 111 successes. Well, in this case, 111 goes over here to 110.5 and over here to 111.5. So that's how we would use the normal curve to approximate exactly 111 successes. Are there times where we'd move the thing to the continuity correction to the right? Absolutely. Let's say I want to know the probability of getting probability that X is less than or equal to 110. Now, when I have 110, or in this case, probability that X is less than 111, same thing. That's the probability that X is less than or equal to 110. So I want this yellow area. Well, 110, I have to scooch the continuity correction to the right in order to get the whole rectangle. So what I encourage you to do when using the normal approximation for the binomial is draw a few rectangles around what you're looking for here. X is less than 111. Draw 111, at least one rectangle above and beyond. If I want X is greater than 110, you can draw 110, maybe you draw even 109 just to make sure, and see where you have to make your continuity correction, which way you have to adjust it, to that half number to encompass the entire rectangle. Now, know this is a little bit longer video, and there's a lot of information in here. I encourage you to watch it again when you have some more time. Try to follow exactly what we did. Review the binomial distribution if you need to, and see if you can meld how we are going to use the normal approximation to calculate binomial probability. And lastly, when you're doing that, you have to make your continuity correction. So you want to draw a couple of rectangles and see where your continuity correction should be in order to get the entire rectangle. Boy, if that isn't enough, I don't know what is. So we'll stop here. Have a great day.